Hi, good morning. My name is Mudawat Lakshman and I am from Computer Science and Engineering Department. Today I am going to discuss the topic Protocol for Multi-Hop Wireless Networks from the subject Computer Networks. Introduction. Wireless networks enable communication without physical connections. Multi-hop communication extends coverage by allowing data to pass through immediate nodes. This is crucial in environments where direct communication is not feasible. Multi-hop protocols are the backbone of such networks, ensuring efficient routing, resource management, and source communication. They are widely applied in disaster recovery, military operations, sensor networks, and IoT ecosystems, where direct communication is often impractical. Understanding these protocols is essential for designing scalable, energy efficient, and secure wireless communication that meet modern connectivity demands. So here, wireless networks enable communication without the need for physical connections such as cables. In many real-world scenarios, direct communication between a sender and receiver is not possible due to the distance, obstacles, and limited transmission power. Multi-hop wireless communication overcomes these limitations by allowing data packets to travel through intermediate nodes before reaching the destination. Multi-hop protocols play a critical role in managing routing, resource utilization, and security in such networks. These protocols are widely used in disaster recovery operations, military communication, wireless sensor networks, and IoT systems where infrastructure may be unavailable or unreliable. What are the basics of multi-hop wireless networks? Multi-hop networks consist of nodes that forward data to reach the destination. The characteristics are dynamic topology, decentralized control, limited resources. The applications are disaster recovery, military networks, and sensor networks. So here, multi-hop wireless networks consist of multiple nodes that cooperate to forward data towards a destination. Each node acts both as a host and a router. These networks are characterized by dynamic topology, decentralized control, and limited resources such as battery power and bandwidth. Since nodes can join or leave the network at any time, routing decisions must adapt dynamically. Typical applications include disaster recovery networks, military communication systems, and sensor networks deployed in remote areas. The evaluation of wireless protocols from 1G and 2G. Here, the evolution of wireless communication began with 1G systems in 1980s, which supported only analog voice communication with poor security and limited capacity. In 1990s, 2G system introduced digital communication, enabling better voice quality, improved security, and services like SMS. Technologies such as GSM and CDMA improved central efficiency and laid the foundation for data services, marking a major step forward in wireless networking. Next, evolution of wireless protocols, that is 3G and 4G. 3G network enabled mobile internet access, supporting applications such as video calls and web browsing with moderate data speeds. Technologies like UMTS and CMDA 2000 played a key role in this phase. 4G networks further revolutionized wireless communication by introducing all IP-based architecture and very high data speeds. Protocols such as LTE and WiMAX enabled HD video streaming, Vivo IP, and advanced mobile applications, significantly improving user experience. And again, the evaluation of wireless protocols, that is 5G and behind 5G and 6G. 5G networks focus on enhanced mobile broadband, ultra reliable low latency communication, and massive machine type communication. They support advanced applications such as autonomous vehicles, smart cities, and large scale IoT departments. Behind 5G and future 6G, networks are expected to enable holographic communication, tactile internet, and AI networking system. These future systems emphasize ultra high reliability, sustainability, and global connectivity through integration with edge computing and quantum computing. Architecture of multi-hop networks. There are nodes, devices that send, receive, and forward data. There will be links, which works wireless connection between nodes. The routing paths are sequence of links used to deliver data across the networks. The architecture of multi-hop wireless network consists of nodes, links, and routing paths. Nodes are devices that can transmit, receive, and forward data packets. Links represent wireless connections between neighboring nodes. Routing paths are sequence of links that data packets follow to reach the destination. Efficient architecture design ensures reliable communication, scalability, and adaptability to changing networks condition. The key protocols are first one AODV and the second one is DSR. AODV, Ad HOC, that is Ad Hoc On Demand Distance Vector, is a reactive routing protocol that discovers roads only when required. Reducing overhead. It is well suited for mobile and dynamic networks such as MANETs. DSR, that is dynamic source routing, is another reactive protocol where the source node maintains the complete route to the destination. It uses route caching and avoids periodic updates, making it sustainable for small to medium sized networks with a moderate mobility. Next, we go for the routing mechanisms. The routing, these are the protocols, key protocols. Here we can see AODV, DSR, OLSR, TORA, that is TORA and ZRP. So there are types also, which is reactive and proactive. There is overhead, how the overhead is, it is high or low or medium or balanced. And they're given a scalability and mobility services also. The routing mechanism. Routing in multi-hop networks can be classified in reactive protocols, proactive protocols, and hybrid approaches that combine both strategies, which is reactive and proactive. So here, reactive protocol discovers routes only when needed, reducing control overhead. Proactive protocols maintain routing information continuously, ensures quick route availability but increased overhead. Hybrid protocols combines the advantage of both approach to achieve better scalability and efficiency. Next, we go for the MAC protocols, that is medium access control. MAC protocols manage how nodes access a shared wireless medium, handle collisions, ensure failed channel access, and the examples are IEEE 802.11, TDMA, CSMA, or CA. We got here MAC protocols control how multiple nodes share the wireless communication medium. They prevent collisions, ensure fair access, and improve overall network efficiency. Common MAC protocol includes IEEE 802.11, TDMA, and CSMA by CA. Efficient MAC design is essential for reducing delay and improving throughput in multi-hop wireless networks. And here, energy efficiency in multi-hop protocols. Energy efficiency is a major concern in multi-hop wireless networks, especially for battery-powered devices. Power-aware routing selects paths and minimizes energy consumption. Sleep scheduling allows nodes to turn off radios when idle, conserving energy. Load balancing distributes traffic evenly to avoid draining specific nodes. These techniques collectively extend network lifetime and support sustainable communication. And we go for security challenges. The security challenges are multi-hop networks are vulnerable to various attacks. The threats are eavesdropping, spoofing, and denial of service. And solutions are secure routing protocols, encryption, and trust managing. Here, multi-hop wireless networks are vulnerable to various security threats due to their open and decentralized nature. Common attacks include EVS dropping, spoofing, and denial of service attacks. To address these threats, secure routing protocols, encryption techniques, and trust management mechanisms are employed. Security is critical for ensuring data integrity, confidentiality, and network reliability. And we go for QoS, that is quality of service. QoS ensures reliable and timely data delivery. The matrices we use are latency, throughput, and packet loss. The protocols must adapt to varying network conditions. Quality of service ensures data is delivered reliably within the acceptable time limits. Key OS matrices includes latency, throughput, and packet loss. Multi-hop protocols must adapt dynamically to changing network conditions to maintain QoS. This is especially important for real-time applications such as video streaming and emerging communication. And next we move on for the case studies. Multi-hop wireless protocols are widely used in real-world applications. In MANETs, they support military communication and energy response time. In wireless sensor networks, they enable environmental monitoring and data collection. In IoT systems, they support smart cities and industrial automation by connecting large number of devices efficiently. And now we go for what are the advantages of the multi-hop protocol. Multi-hop protocol extend network coverage without requiring additional infrastructure. They improve scalability by allowing large networks to be formed dynamically. These protocols enhance reliability by providing alternative routes in case of node failures. They flexibly making them suitable for diverse and challenging environments. The limitations of challenges. What are the limitations and challenges? The routing overhead, increased latency, mobility induced route failures, limited bandwidth, energy. These are the limitations and challenges. Despite their advantages, multi-hop wireless networks face several challenges. Routing overhead increases due to frequent route discovery and maintenance. Multi-hop communication introduces additional latency. High mobility can cause frequent route failures, limited bandwidth, energy constraint. Further, for complicate protocol design. And now we move for the conclusion of the slides. Multi-hop wireless protection or protocols are the backbone of the modern decentralized communication system. They enable data transmission over multiple nodes, extending coverage and improving network resilience. By balancing efficiency, energy consumption, and security, these protocols support critical applications such as disaster recovery, military operations, IoT, and smart cities. Understanding these protocols is essential for designing future wireless networks. That's it. Thank you.